Assalamualaikum, my name is MUHAMAD bin RAZAK and our group will conducting linear conduction experiment. So first thing first, we open the switch and then we open the pipe. After that, we open the power for heater. We wait for several minutes and after that we will increase the power to 30 watts. So this is stainless steel material. We wait for several minutes so the temperature will stabilize, and this is the wire for each thermocouples. After we get the data for stainless steel, we change the middle to stainless copper and brass.
Assalamualaikum and a very good day for our viewers. Today, for heat transfer, we are going to look at Lab 1 linear conduction. Before going any further, let me introduce my group member. Our team consists 4 people, me, Muhammad IRFAN bin Muhammad SHUKRI, MUHSIN AMILI bin NOOR, RUSHAN anak lelaki Ranganathan, Muhammad AIMAN bin RAZAK. So today, we are going to explain in depth each part of the lab. So as you can see, this table of content in our slide. They have theory, objective, equipment and apparatus, procedure and methodology, safety and precaution, result, discussion, and conclusion. For the theory, what is linear conduction? The linear heat conduction simulates one-dimensional, steady-state heat transfer in the axial direction of an axisymmetric composite solid. Exterior wall radial direction are insulated. According to Fourier law of heat conduction, if a plane wall of thickness and area support a temperature difference, then the heat transfer rate per unit time by conduction through the wall is found to be. If the material of the wall is homogeneous and has a thermal conductivity K, the constant of proportionality, then it should be noted that heat flow is positive in the direction of temperature fall, hence the negative sign in the equation. For convenience, the equation can be arranged to avoid the negative sign as follow the formula. As you can see, this is a formula. So, next is the objective for the experiment. First is to show how different material in contact can affect linear heat transfer. Second is to determine the constant of proportionality, the thermal conductivity K, for one-dimensional steady flow of heat. Third is to compare how to calculate thermal conductivity for material. Lastly, to show how thermal paste help to give a good thermal connection. For equipment, linear heat conduction, it is a compact bench mounting frame that connects to a suitable electrical supply and a cold water supply and drain. It supplies safe, low voltage electrical power to the heater in the optional experiment and show the temperature of the thermocouple in each optional experiment. The cool water circuit is simply the incoming main cool water supply that pass through the optional experiment unit and then out to the drain. A hand-operated valve in the water circuit allow you to control its flow. So for linear heat conduction, they have two displays show the heater power and the temperature of the thermocouple in the optional experiment. So next is safety progression in lab. As you can see, no food or drink are allowed in lab. Proper PPE and lab attire to be worn at all times. Stay focused and aware of your surroundings. Don't play around in the work area. Ensure work area is clean and tidy during and after work is done. If there is any accident, inform to the engineer in charge. Check all joint and connection before starting the lab work. Follow all safety operating procedure equipment before starting work. Wear gloves when handling any heat. Maintain safe distance and sanitize hands before and after using equipment.
Hi, a very good day. My name is RUSHAN. I'm from BMMH section 2. Today for the heat transfer, we are going to look at linear heat conduction experiment, which is done using the brass middle section. Okay, for the experiment, the ambient temperature is around 25 degrees Celsius and the power range is from 30 watts to 90 watts. And then we can also see the distance from the power from the heating source, which is T1 to T7. Okay, let us look at the first row. The first row, the power is around 30 watts and the T1 is 334.6, followed by T2 at 329.7, T3 at 325.1, T4 at 319.1, T5 at 314.2, T6 at 309.9, and T7 at 305.8. And all of this is in the unit Kelvin. Next, we shall look at 50 watts. Okay, for 50 watts, the T1, which is very close to the power source where the heat is emitted, you can see at T1 is 343.8, at T2 is 336.4, at T3 is 330, T4 is 322.2, T5 is 316.2, at T6 is 311.2, and T7 is 306.6. And at 90, you can also notice that when it's closer, it has a higher temperature, which is at 364.1 Kelvin. And further from the heat source, which is at T7, there's a large difference where the temperature is around 309.5 Kelvin. Okay, you might be wondering why the temperature further from the heat source decreases. This decreases because when further the temperature decreases, this is due to when heat transfer is from a hot region to a cold region, and it is also further. And you can also see the distance from T1, which is at T1, which is the actual heat source, which is at 0, T2 is 0.02, T3 is at 0.04, T4 is at 0.06, T5 at 0.08, T6 at 0.10, and T7 at 0.12. Okay, next we shall look at the temperature against distance graph for the brass middle piece at 30 watts power. Okay, from the graph we are able to see the further the distance is, the lesser the temperature, and this can also be seen from the gradient. Next, we shall look at the temperature against distance for brass middle piece at 50 watts of power. Here, the same concept applies. The further the heating, further the heating source, and the distance increases, the lesser the temperature. And this can also be concluded by using the Excel and getting a gradient. This is a temperature against distance graph for brass middle piece at 90 watts of power. Okay, next let's look at the middle section material for stainless steel. The ambient temperature from the previous material is also 25 degrees, and hereby we have also conducted by using a wide range of power from 30 watts to 90 watts. Okay, when you look at the table, you are also able to identify the further the distance, which is at the third row, the further the distance from the heating source, the lesser the temperature. Okay, because for example, this is a heating source and you are standing here. Okay, because you're far from the heating source, you will feel lesser heat, and when you're near to it, you'll feel it getting more hotter. And different materials also have different thermal conductivity. Hereby, the rate of transfer of heat from the hot region to a cold region is lesser, or sometimes it might also be increase. Okay, hereby we can also see the temperature against distance for 30 watts of power by using the stainless steel material. Okay, after plotting all the lines, we are also able to get the gradient from the Excel. And when you look at here, the gradient is around 184.64. Okay, next is the temperature against distance for stainless steel middle piece at 50 watts of power. And consequently is the temperature against distance for stainless steel middle piece at 90 watts of power. Okay, now let us look at the third experiment, which is the middle section has been changed to stainless copper, and the ambient temperature stays at around 25 degrees Celsius. This is just a rough estimation, as we have not used any thermometer or some other measuring equipment to get the ambient temperature. Well, when you look at the power, it follows the same range, which is from 30 to 90 watts, and the distance is from 0 to 0.12 meters. And when you look at column 2 to column 2 to 7, you can see T1, T2, T3, T4, T5, T6, T7, which is the temperature from the heat source. Okay, when you're looking at T1 is directly near the heating source. Okay, it has a very high temperature, and when you look towards your right to maybe T4, T5, T6, T7, the temperature decreases. And as I explained just now, it also follows the same principle, where conduction occurs through a distance at a very longer time. The more closer you are to a heat source, like I explained using this just now, the more closer we are to the heat source, we will feel the heat more, and the further we are from the heat source, the heat is less. For example, linear conduction. Okay, but let us look at conduction. Okay, when water is boiling, you place your hand nearer to the kettle, you'll feel it very heaty. But once you take your hand further, you might just feel a slight heat. The same thing applies to this linear conduction as well. Well, for the results, let us look at the temperature against distance for stainless copper middle piece at 30 watts of power. Okay, we have done a graph at the side, and also a table at the side, and also a graph which indicates the temperature and distance, which then we have also calculated the gradient in the graph. Okay, this is for 50 watts of power, temperature against distance for stainless copper middle piece. Next is the temperature against distance for stainless copper middle piece at 90 watts of power. For all this graph, we have also calculated the gradient. Okay, for the previous data, when I talked about gradient, okay, gradient is the ratio of difference, temperature difference between a given length, and since it's a linear thing, so the red thing is the heat source, and this is the line where the temperature will be different, maybe from point A, point B, or point C.
Hello, Assalamualaikum. My name is MUHAMAD bin RAZAK, and I will explain about our linear heat conduction experiment results with stainless copper as middle section. So this table shows the result that we gain from the experiment. This is the graph of temperature against distance for stainless copper when we set the power to 30 watt. As we can see, the graph is directly proportional and have negative slope with gradient negative 165.18, and then when we increase the power to 50 watt, the gradient is negative 315.89, and after that, when we increase the power up to 90 watt, the gradient is negative 429.11. This is the graph of temperature against distance for 30 watt for each material. So for the brass, the gradient is negative 244.46. For stainless steel is negative 184.64, and for stainless copper is negative 165.18. What does this mean? Alright, a temperature gradient is physical term that describe how rapidly and in which direction the temperature change in each area. The temperature gradient is a three-dimensional quantity measured in Kelvin per unit length on a certain temperature scale. According to the law of heat conduction, often known as Fourier's law, the rate of heat transmission through a medium is proportional to the negative gradient in temperature and the area at right angles to that gradient through which the heat flows. It means that temperature gradient is the ratio of the temperature difference between 2 points to the distance between these 2 points.
Assalamualaikum, my name is MUHSIN AMILI. Today I'm going to present the discussion number 2. So for discussion number 2, use the furthest reading T1 and T7. The given distance between them, the heater power and the bar area with the equation 5 to calculate the thermal conductivity of the metal bar. Compare it with the typical value given in table 1. Explain the cause of any error for the different value of the theoretical and experiment thermal conductivity. So for the first calculation, we are going to use the brass for 50 watt. For the D1 is 343.8 Kelvin. For T2 is 306.6 Kelvin. For the lag is 0.12 meter, and the diameter is 0.055 meter. So we have to calculate the area using pi r square. But in the equation, we get 2.376 times 10 negative 3. So we have to calculate the thermal conductivity value using the 50 watt times the meter length 0.1 over area times the temperature difference. We get 67.88 for the calculated value, and the typical value for brass is 123. For the next material is we are using stainless steel. For the T1 355.3 Kelvin. For T2 is 311 Kelvin. For the length is 0.12 meter, and the diameter is 0.055 meter. So we calculate the area on 2.376 times 10 power of negative 3. So we have to calculate the thermal conductivity value for the stainless steel using 50 watt times 0.12 meter. over area times the temperature difference, we get 57 for the thermal conductivity for the stainless steel. For the typical value of the stainless steel is 16. Next is the stainless copper material. For the temperature, T1 we got 346.9 Kelvin. For T2 we get 308.4 Kelvin. And for the length is the same, is 0.12 meter, and the diameter is the same to 0.055 meter. So we have to calculate the area again. We get 2.376 times 10 power of -3. Then we are going to calculate the stainless copper thermal conductivity. 50 watt times 0.12 meter over area times the temperature difference. We get 65.59. For the typical value of the stainless copper is 386. So we can see from the previous calculation, we get the calculated thermal conductivity value is different from the typical value. The error may happen during the experiment is the thermal energy is lost to the surrounding. Thermal energy refers to the total energy of all molecules within objects. Heat is the amount of energy flowing from one body to another spontaneously due to their temperature difference. The transfer of energy as a heat occurs at the molecular level as the result of the temperature difference. When a temperature difference loss does exist, heat flows spontaneously from the warmer system to the colder system. As a result, any object hotter than surrounding must continually lose a part of its thermal energy. This is a natural behavior of all objects.
For third question in discussion, what can you observe from the gradient of the chart for each heater power setting? First is, this might apply to all of the material that have been tested. As you can see, different type of material also affect different temperature, whether it is rise or drop. Then the estimate gradient show a decrease. We can observe from the gradient that the temperature is decreased with increase in distance. Next is, in terms of the heater power setting, the higher heater power level and the higher temperature for all angle. So lastly, our prediction for this experiment is temperature can decrease more than 0.14. It is because the length can affect the temperature. That's all from me. Thank you.
Discussion number 4. Add a best fit line through all the results to find the overall thermal gradient. From the overall result, find the thermal resistance R value for the whole bar. Then use the thermal resistance in series method to find R and the K value for the middle section. Use the K value you found from the first positive for brass section side of the middle. So for this discussion number 4, we have to calculate the brass resistance. So for this calculation, I am using the 50 watt data. So the T1 is 343.8 Kelvin and T7 is 306.6 Kelvin. For the thermal conductivity, we calculated before, we get 67.88. The resistance formula is L over K times area. So first we have to calculate the R brass, or resistance for the brass. 0.02 over 67.88 times 2.376 times 10 power of -3, we get R brass 0.124. Then we have to calculate the R total. T1 equal to T1 minus T7 over power. So we plug in the data in this equation. 343.8 Kelvin minus 306.6 Kelvin divided by 50 watt, we get 0.744. For the RMID, we have to calculate using the R total minus 2 times R brass. So for the R total is 0.777. This R total is 0.744 minus 2 times 0.124. We get 0.496 for our RMID. Then we are calculating the KMID. The KMID formula is LMID over RMID times area. The value of LMID is 0.02 divided by 0.496 times 2.376 times 10 power of negative 3. We get 16.97 watt per meter Kelvin.
Okay, conclusion. So based on this experiment, we are able to learn heat transfer concepts such as conduction, convection, and radiation. Through the lab, we are able to apply basic laws of heat transfer by conduction through cylindrical solid to be investigated. We are also able to apply Fourier's law to solve missing parameters in the experiment to segregate the data academically. And also this lab enables us to understand on how heat conduction uniformly around a solid disk of uniform dimension. And lastly, we are able to prove that thermal conductivity is inversely proportional to the temperature regards to distance. Thank you.